Hi, everyone. Thank you for joining this session. Today, I'm excited to present to you our work on a new infrastructure called Ad hoc blockchain, an ad hoc blockchain designed for private, quantum secure barter scenarios. This work is a collaboration between researchers from Ben Gurion University of the Negev, Israel, and Google. Our project addresses the growing need for secure private asset exchanges across multiple blockchains, especially in a world heading toward quantum computing. I'll take you through the motivation, technical innovation, and implications of the system, and ensure the explanations remain as much as possible intuitive. Let's begin with a motivating scenario. So let's say we have Alice and Bob, who are very concerned about their privacy. We have Alice, who owns 10 Sol on Solana, and Bob, who owns a unique car, which is ownership is represented as an Ethereum NFT. Let's say Alice and Bob both had their assets on Ethereum, so they could just use a smart contract if they would want to trade these assets. But Alice is on Solana, and also the contract will be public, and Alice and Bob are very shy. If, let's say, Alice and Bob in a different scenario would want to swap coins across blockchains, they could use a bridge, but that would mean that they will need to trust a system, an external system to handle the swap for them. But the system is also external, and also it supports only specific coins and assets and specific networks. So that's a different scenario. And let's say another scenario, um, if they wanted to trade a physical item for digital money, they can use a third party or a regular physical contract like we have today in every country. But this isn't a direct barter, and it won't necessarily be atomic. What is atomic? It means that either the barter happens fully, Alice gives Bob what he wants, and gives Alice what she wants, or nothing happened at all, and everything stays the same. So in this case, Alice and Bob want something a little bit different. They want to swap a specific NFT on one chain for tokens on another, and also use external data to confirm the swap. So let's see the exact case. They want to barter directly without centralized exchange. So let's see a little bit of the requirements of the trade that they want to do, the barter they want to do. First of all, they want the business logic of the barter to completely stay private. Next, Bob's car should be inspected in a garage that will come into as a blockchain oracle. The barter must be atomic, as I mentioned before. We don't want Alice to give Bob the money and Bob running away with the money and the car, or the other way around. Additionally, we want the barter to be secure against all kinds of attacks and cryptographic primitives. And we don't really want to leave any permanent traces about the barter that happened, about the logic specifically. Also, the barter must be resilient to malicious servers, and we will see how we will handle all of these next on. So let's look at the system overview. First of all, I'll start with an explanation about what is an ad hoc blockchain. So an ad hoc blockchain in general is a temporary blockchain that we build for a short amount of time for a specific use and then delete it. So let's see how we use this in our system to allow Alice and Bob do their barter securely and as they wish. So we operate in three phases. The first phase is coordination of the configurations. That means that we want Alice and Bob to coordinate and agree about what is going to happen, what are the terms, how is it going to execute, and all kinds of daisy stuff. So they both, let's say, talk and approve about like all the configurations. And then we have the setup phase. In the setup phase, let's say on public blockchains like Ethereum and Solana, assets are locked using hash time lock contracts until a specific secret signatures, pre-images, are revealed. So Alice and Bob both lock their assets on the public blockchain, and then they initialize and run the ad hoc blockchain that will operate the barter securely. So the last phase is execution or trade. So here we have a few steps. The parties distribute shared secret shares to the ad hoc blockchain servers of the pre-images, and then the ad hoc blockchain verifies everything and execute the private barter logic. And if all conditions are met, it releases the pre-image to the hash time lock contracts, and the locked assets are released. Let's dive a little bit into that to better understand it. It is important to say that the entire process of the ad hoc blockchain stays off-chain and it is erased after completion. So, phase one, coordination and commitment of barter configuration. Let's see what we have in phase one. Okay, so first of all, we have this diagram that maybe helps us represent what we see here. On the left side, we can see the configurations that Alice and Bob need to agree about. I will just in a moment explain what we see here. And a little bit to the right, we can see the ad hoc blockchain configurations that includes which servers Alice and Bob trust to run the ad hoc blockchain, their cloud provider, their node version, and etc. etc. Additionally to that, they also define the business logic smart contract, and on the left side, we come back to that, the contracts config, the hash time lock contracts. So let's see step by step what do we do in the coordination step phase. Okay, so first of all, each party, Alice and Bob, writes a hash time lock contract that locks their asset until a secret they generated is revealed. So we can see here on the left side these two hash time lock contracts, A and B. Let's look for example on A. So A states that it's waiting to receive a pre-image of SHA-256 on signature A. That signature A, it's something secret that only Alice has. And if the pre-image is received, it transfers the asset, the 10 SOL to Bob. Otherwise, if we have some certain time that the barter should be canceled, the asset is coming back to Alice. And the same thing for Bob. They have a contract that waits to get a pre-image of some secret that Bob unhash on a secret, and sorry, and only when it gets this pre-image, so it releases the asset to the other side. We can also look at the business logic smart contract here, but we can dive into that a little bit later. So let's see if we have some more information here that we need for the next slides. So we call SIG A and SIG B the pre-image. This is the complete secret that if it's revealed, the assets are transferred maybe before time. So we cannot reveal them before time. It is really important. And what we put on the contract is the SHA value on them. So it doesn't reveal anything about the signature because it's one way. But it does guarantee that only whoever has this pre-image can send it and release. So the parties agree on all the configurations. We can continue. Then we have the second phase, the cryptographic setup protocol. So let's see what is happening here. First of all, both Alice and Bob deploy the hash time lock contracts they wrote and agreed on before, each on their network, and they lock their assets. Alice locks Tensor, and Bob locks the vehicle NFT. Then the parties initialize the servers, initialize the Alloc blockchain with assigned configurations. And lastly, the servers starts to run and verifies themselves. They verify the signature of Alice and Bob on the configurations and whatever is needed for a, let's say, secure boot. And lastly, they deploy the barter smart logic contract in their own ad hoc blockchain, actually. So let's get to the interesting part. How this barter happens and what is gonna happen here. So, phase 3, the first thing that happens in this phase is that Alice and Bob send secret shares of their pre-image to the servers. Now, it might look just like one arrow here, but actually, let's say Alice, she takes her SIG-A, which is the pre-image, which is top secret, because if the SIG-A is revealed, if the pre-image is revealed, the assets are running away from her, even if not all the conditions are met, and maybe the garage didn't check it yet. So she needs to keep it secret, and as well the ad hoc blockchain. So I forgot the word, sorry. She sends the server the secret shares of her pre-image. Each server gets only one. We see here 4 servers, but it's not the real. It's not the real number. It's just for diagram purposes. And additionally, she sends a hash value on the pre-image, just like in the contract, actually. The same thing Bob does. Now, after that, the business logic starts running. What does it do? First of all, it validates the pre-images, the signatures of Alice and Bob. We will see later how are we doing this without revealing anything about the signature, because we said if we reveal the signature, the barter is it's not secure anymore. So we're gonna dive into that later. It's really interesting, actually. And then the business logic continues. We have some conditions there. We wait for a signature approval from a garage that the vehicle is okay. And finally, when all the conditions are met, the ad hoc blockchain release the shares, the pre-images, and reconstruct them to one pre-image or two, one for each side, and sends it out to the hash time lock contracts. And once they arrive to the hash time lock contracts, the assets are unlocked and sent to the other side, like we see here in point 5. Okay. Now, let's see how we do this, how we send the secret shares, but still the ad hoc blockchain servers are able to verify them without knowing. So, of course, we're going to use multi-party computation zero knowledge proof verification. I'll just say a word about multi-party computation. These are such algorithms that allow us to compute distributely on different servers. And let's see how we utilize this in our system. So we are using multi-party computation in the head, or in short, MITH, zero knowledge proof validation of XOR-based secret sharing. Let's dive into that. So let's see what each party does, Alice and Bob. So each party create the secret pre-image. Let's look at Bob for now because it's red. So Bob creates the pre-image. Then he sends XOR secret shares of the pre-image to the ad hoc blockchain servers. We represent it here as XB1, XB2, etc., etc. Lastly, he publishes the commitment, the hashed pre-images, to the ad hoc blockchain, like we saw in the hash time lock contract and in the diagram before. He sends a SHA on the pre-image. Let's continue. Now, each server calculates the hash value on the secret share that he got. So let's say server number 1 got XB1. So he calculates a SHA on XB1. Now, the next step is that he hashes the output and commit it. So he hashes whatever we have here. So actually it's like hash on the secret share. Now, it's important to notice that the server's commit of the hash of the secret share is a secret share of hash on the pre-image, only if the secret share is valid. But it's important to see that we have a relation between something that includes the secret share alone to some computations. It relates to the same computations on the pre-image. And this feature will allow us to do some more interesting stuff. So let's see them. So let's see how the verification workflow continues. So now after each server computed his own stuff, the servers together jointly starts reconstructing all kinds of information, but I will say in advance, they still never saw the pre-image itself. It's always SHA on the pre-image. Okay, so the pre-image is not revealed at any step until I will say it will be revealed, and spoiler alert, it will be only when all the conditions are met. So first thing they do is they reconstruct the hash secret shares. So they post together one to another the hash on XB1 until a hash on XB on the last secret share, and they receive SHA or hash on what is allegedly supposed to be the original pre-image, if everyone is honest and Bob is also honest and sent the correct shares. Then it compares it to the party's commitment, because Bob sent us before. We saw this already, at least at 2 places. So they first of all compare it, and if it doesn't compare, they say, okay, bye. And if it's okay, so they continue. Let's see how. So the second thing they do is that they reconstruct the server's commitments. So what does that mean? They take the hash on each secret share, they post it, and then they reconstruct it, and they get hash on what is supposed to be the pre-image. Now, they compare this as well to the hashed party's commitment. So they just do hash on the party's commitment, and they compare the two. If they are both okay, so that means that we got valid secret shares from Bob, and that we can continue. So, as I said before, until here, each server processes its shares only. No servers sees the complete pre-image. Now, only if the comparison is valid, the servers and all the conditions are met, the servers reconstruct the secret shares and receive the pre-image. Lastly, just a second after, they reveal it, and then the contract, the hash time lock contract, are released, and the funds go to their way. Now, we want to run each instance of this MPC execution on 3 servers. We can call them triplets. So we use triplets of servers for each MPC instance to keep things simple and reliable. Each triplet manages a commitment linked to a preimage. When the ad hoc blockchain logic says it's time, that preimage is revealed. So, what happens if some servers are malicious or simply fail? This is the Byzantine generals problem applied to our settings. So, what is the problem? We want to handle bad actors. The first part of the problem is that the triplets of Byzantine servers, sorry, it's the other way around, that a single Byzantine server can block an execution and therefore won't reveal the preimage even if all the conditions are met. So we do not want that. And second, triplets of Byzantine servers can cause the locking contract to release assets before time prematurely and reveal the signature before all the conditions are met. So we do not want this as well. Let's see how these scenarios look like. So the first part that I mentioned of the problem, let's say we have here 3 servers. The green ones are honest and the red one is malicious. And the red one can alone block the execution of the whole triplet of servers. So we do not want that. The second part is let's say we have a triplet. Full 3 out of 3 are malicious. So they can jointly prematurely reveal the signature, and then the funds may be going without the conditions to be met. So we don't want these 2 at all. Let's see what is our solution. So the first part of our solution is to not just run one instance of MPC. We can run a lot of instances of MPC. Let's see how it looks like. So this is how it looks like. Sorry. We have here is an example of 9 MPC instances or 9 triplets where we have 6 Byzantine servers. We can see that 3 of them are in the same triplet and they do a premature reveal, and the other 3 are just blocking executions. So we will see how will we manage that and overcome these problems. And the second part of the solution is to add something to the smart contract. So we had a threshold of the number of pre-images that we need to receive in order to release the funds. So we will call this number R. R is the sufficient number of pre-images that are released. That is safe to say that the hash time lock contract released the asset on time. And we will soonly see what is R and how do we compute it. Okay. So let's talk a little bit more mathematical. We assume that we have a bound for tolerating up to T Byzantine servers. Okay. So we will denote T, we just said that, and R is the minimum number of outputs of triplets needed to safely trigger the hash time lock contracts. Now, how do we prevent blocked executions? Or let's talk about numbers in that case. So if each Byzantine server can block up to 1 triplet execution, that means that in total, up to 3 triplets may be blocked. Now let's talk numbers about the second part of the problem. If we want to guarantee at least one correct or mature reveal. We want to guarantee that we ask for enough reveals that at least one of them will be not premature, which means that the global asking is not premature. So let's look into this. Each triplet of 3 out of 3 Byzantine servers can cause a premature reveal, as we said. So that means that only up to t divided by 3 rounded down, Byzantine triplets can do this, can premature reveal. So we will set R to be the maximum number of triplets that can premature reveal plus 1. So we will always have at least one premature reveal, which means that if we require R preimages, we will be safe that for sure it is not premature and it's not before time. So now, the total required triplets, if we want to ensure we get R valid outputs, despite T blocked executions, we need to run at least R plus T, which is T plus T divided by 3 plus 1 triplets. So let's see how these worst case scenarios look like. Here we have an example of 9 MPC instances, 9 triplets with T is 6 Byzantine servers. If we calculate, we get that R is 3. So on the left side, we can see the worst case of maximal blocked executions. Here we have 6 blocked executions, but let's remember, we asked for 3 honest executions in order for the system to continue operating and the hash time lock contract to release. So we still have 3 honest executions here. So we are fine and we can still operate despite the blocked executions. And the worst case in terms of premature reveals, if all the Byzantines are together in triplets, so we have here 2 premature reveals, but we required 3. So at least one of the required executions will be mature, which means that nothing will happen before time. So let's see what are the benefits of the ad hoc blockchain architecture. So first of all, private and confidential cross-chain barter. The system allows business logic privacy and forward privacy, which means that the contract logic remains hidden during execution and no traces of the barter logic persists after execution. We also allow atomic execution, which means that assets are released only if all contract conditions are satisfied, either completely or not at all. And the last part, the execution correctness is proved while preserving confidentiality of secrets via zero-knowledge proof and MPC in the head, multi-party computation in the head. Now, for the second aspect, we enable complex conditional logic. We allow cross-chain support and asset flexibility. We support multiple blockchains involving any assets, NFTs, tokens, or representations of real-world goods. We also allow customizing logic for conditional swaps, supporting any contract terms, including time and multi-step logic, whatever you want. And the third thing is real-world event triggers. Barter logic can depend on real-world events like from Oracle inputs. Let's say, for example, in our example in Alice of Bob, we want to receive an input from the garage inspection. So, and the last aspect here is security and reliance. We are perfect information theoretic secure, and we guarantee that with MPC protocols. We don't assume any number theory assumptions. We have post-quantum security because we are built on post-quantum cryptographic primitives like multi-party computation, and we are Byzantine fault tolerant, and the protocol remains running correctly even if some ad hoc blockchain servers misbehave. So let's start to finish up. Ad hoc blockchain is the first system that enables truly private, quantum-safe, cross-chain barter with complex business logic. So what are our immediate applications? Ad hoc blockchain has immediate applications in the blockchain space that includes private and atomic cross-chain asset trading, confidential business agreements, and quantum-safe smart contracts. For broader implications, the technique we've developed, for example, the distributed multi-party computation in the head in our terms, provide a template for building privacy preserving blockchain systems that will be secure even in the quantum computing era. We're not just solving the technical challenge of private cross-chain barter. We're creating a foundation for Web3 private and secure barter infrastructure. What are our next steps? They might be a little bit obvious, but to open source implementation and to have some industry partnerships. Overall, this technology has the potential to revolutionize, I'm sorry, I can't pronounce that, how we conduct secure and private transactions and interactions in the blockchain and Web3 space. So thank you very much for your attention. If you have any questions, feel free to contact me through my email or my LinkedIn. I'll be happy to hear comments or to answer more questions. And hoping for better days and to see you soon. Thank you very much.